We previously discussed how we can decrease the rate of heat transfer from a surface through insulation. Now we are going to discuss how to do the opposite. That is, how to increase the rate of heat transfer from a surface. This is the formula for the total rate of heat transfer from the left surface of the wall to the fluid surrounding the right surface of the wall. Two thermal resistances are involved in this formula. The first is conduction thermal resistance due to the wall itself, and second is the convection thermal resistance due to the thin film of air surrounding the right surface of the wall. We can see from both formulas that the conduction and convection thermal resistances are indirectly proportional to the area perpendicular to the heat flow. This means that increasing the area normal to heat flow will cause the conduction and convection resistances to decrease, which will then increase the rate of heat transfer from the surface. Now the question is, how do we increase the surface area from which heat can flow? A solution to this is by installing fins on the surface of the object. You have probably seen a fin surface before without even realizing it. Fins are widely used to increase heat transfer from the condenser tubes of an air conditioning unit. This is the primary purpose of the parallel vertical rectangular plates placed on the surface of the condenser tubes. These plates are called fins. Now let us analyze how heat is transferred through a fin. First, we shall take a differential volume element inside the fin and analyze the thermal energies coming into and out of this element. From the given figure, we can write the energy balance equation for this differential volume in this way. The rate of heat conduction going out of the differential volume is given by this equation, where A sub c is the area normal to heat flow. This can be computed by multiplying the width of the fin by its thickness. Now the rate of heat convection from the surface of the differential volume can be computed using this equation, where P corresponds to the perimeter of the fin. This can be computed by adding twice the fin width to twice the fin thickness. Now by substituting the formulas corresponding to the three thermal energies in this equation, we will arrive at this equation. The formula which characterizes the variation of temperature within the fin is only applicable under the assumption that the thermal conductivity of the material and the area normal to the heat flow remain constant all throughout the length of the fin. Now by introducing the thermal parameter theta in the equation, which corresponds to the temperature excess, and replacing the coefficient of T minus T sub infinity in the second term of the equation by m squared, we will be able to simplify the resulting equation into a second-order linear differential equation. Now we have studied in our differential equation course how to solve differential equations of this form. And we have also discussed that the general solution for a second-order homogeneous linear differential equation has this form. The general solution gives us the formula for the temperature excess theta at any point within the fin that has a distance of x from the base of the fin. Remember that the temperature excess is simply the difference between the temperature of a point in the fin and the temperature of the fluid surrounding the fin's surface. Now, obviously, for us to compute the values of the arbitrary constant in this equation, we need to know two boundary conditions. The first boundary condition is the temperature excess at the fin base. This can be computed by simply subtracting the surrounding fluid temperature from the fin base temperature. On the other hand, the second boundary condition is based on the condition present at the tip of the fin. We have 4 cases from which we can base the second boundary condition, and this will be the subject of our next video.